this is how I forecast for severe weather. And severe weather is just a general saying of just a severe weather such as hail, damaging winds, or tornado. And these models, these weather models, are what I use to forecast for them. I use specifically the HER, the NAM, the NAM-NIST, and the GFS are the ones that I use. The HER is a short-range weather model that can see anywhere from 18 hours into the future to 48 hours into the future. And they release long model runs on the 18, 12, 6, and 0Z runs. And for example here, we are looking at Tuesday at 2 o'clock in the afternoon. And considering I'm on Eastern time, the 18Z to me is 2 o'clock, because 0Z is 8 o'clock, and it can be kind of weird at times trying to remember and that kind of stuff, but it's really fine. The one I use is the NAM-NIST. This is a weather model used for 3 to 4 days into the future, and for example here I'm looking at the simulated reflectivity for Wednesday afternoon, and I can see here there's a band. It seems like just a system of thunderstorms anywhere from Illinois and Indiana all the way to the Carolina coast. And what I check on these models specifically is I check the big ones are dew point, and usually I want to see at least a 65 dew point or higher for thunderstorms. 70 is most ideal in the summer, but usually in the spring months you usually don't have a 70 dew point unless you're very close to the Gulf of Mexico. So in this case you'd be wanting to look for 65 dew points or higher, and it appears I have around 68 dew points, so I seem like I'm going to get some storms on Wednesday. Another one I check is the CAPE. CAPE stands for Convective Available Potential Energy, and is how easily lifted the air is. It usually takes about 1,000 CAPE to make a thunderstorm, and in this case I have around, right around 1,000. See, I might get some storms on Wednesday. And the other two big ones I check, and these are mainly for severe storms and tornadoes only, I check the Helicity Rates. I don't know quite what Helicity Rates are. It's shear of some kind in the atmosphere. It may be something along those lines. And I check the 3 kilometer helicity and the 1 kilometer helicity. Usually for storms or like stronger severe storms, I usually want to see at least 100. And another one which the NAM-NIST doesn't have is something on the NAM, and that is mid-level lapse rates. Mid-level lapse rates are the rate of cooling as you go up into the atmosphere. It's the rate of cooling per kilometer. For example, here it is 7.4 Celsius per square kilometer as you go up into the atmosphere. And whenever you put this into play with storms, it makes updrafts more robust, more intense lightning because more friction with different types of precipitation. It can also be a big one with hail as well. So mid-level lapse rates are a big one that you really want to pay attention to when trying to forecast for strong to severe thunderstorms. Is by going to the simulated reflectivity, and you pull up the said time you want to go to, and you look at, okay, there's a good one. You look at this. And this can also help you, because of how high resolution it is, it can also help you what types of storms are going to occur. For example, there is a strong single-celled storm down here near Lincolnton, and there's a complex of thunderstorms to my north near Taylorsville and Lenore and Statesville and Salisbury, extending along the I-40 corridor. And, for example, there's a bunch of discrete storms up here that may have a potential tornado threat at that. And then there's a cluster of storms down here, and these storms are moving in all sorts of different directions, and you can loop it to find out what directions they're going. You can also look at how the total rainfall, like here there's a big corridor of 5+ inches of rain. some of these models can be extremely useful at times whenever trying to forecast for severe storms. The final one that I look at for the most part is the GFS. And I use the GFS, and I usually look at it on the general US. The first thing I look at is the moisture, which is the dew point. And usually I want to see at least a 70 or higher. It's usually generally based upon the time of year. For example, summer you want 70 or more, and then spring you want 65 or more, and then winter you want like 60 or more. And looks like here we have the moisture, and then another one I checked is 850 millibar winds, which Ryan Hall refers to as NATO juice, which is the low-level jet, which can help spin storms into more dramatic shapes and can help the lower level spin enhance so you can get more tornadoes, which in this case we don't have a whole lot of shear. Usually I'm looking for at least 25 knots whenever looking for supercells. You can also check too if the shear, for example, we're going to look at this specific area right here over northern Alabama. You go from the 850 millibar winds to the 700 millibar winds, and then to the 500 millibar winds, and if there is still a layer of shear over that entire area and it remains strong, you consider that deep layer shear. And when forecasting for supercells tornadoes, deep layer shear is always what you're looking for. Another one you can use to gauge like sort of the general probability of supercells is you can use the Supercell Composite, which is it's looking at a bunch of the factors and it's determining them all into like a big math equation, and it's coming out with a number of like the sort of probability of a supercell. For example, here there's like in central Oklahoma there's like a 3, and the parameter goes from like 0.25 all the way to 35 being on the very, very high end that you see rarely. And you can loop it, and it is a useful parameter when looking for severe weather. Something to consider though with all this is, and I'm going to go to the NAM for this, I'm going to pull up my forecast region, Mid-Atlantic, and I'm going to go to here. I'm going to click on Wednesday, and I'm going to go to my general forecast area, and I'm going to click and hold, and I'm looking for the projected weather balloon sounding. Soundings are quite devious to try to read over time. It takes time to learn them, and in this case, CAPE is how easily lifted the air is. CINH is the capping inversion, which is like an inversion layer that can suppress all storm development for the said time period. Anything that's more than 50 or 100 you do not want to see on a storm day because it will suppress and kill all storms. And the LCL is lift condensation level. It's meaning how high the storm's bases are going to be. In this case, are around 1,100-ish feet, meaning this would be a good day for damaging winds, or it's usually not tornadoes. Usually these tornadoes have much lower bases, so they don't have such a long way to go from the storm's base to the ground. And the LI is just its lift. And for this, you want as high of a negative number as possible. Usually anything from higher than -5, you have a sufficient amount of lift for storms. And I'll come back to CINH here. Usually you want the number as close to 0 as possible, I'll note. And here you have surface 1 kilometer, surface 3 kilometer. These are helicity rates. And like I said, you want 50 on the 1 kilometer and at least 100 on the 3 kilometer. In this case we're running low, and the one shear layer that matters mostly is the effective shear. I'm not sure what that stands for, but this is the important one, and that is 16 knots of shear, meaning I don't have a whole lot of shear in this atmosphere, and storms are going to be fairly limited, and the potential hazard type is just a marginal severe, which I think is probably correct. And also here you can look at your hodograph, and it measures what the atmosphere looks like as you go. The green line is dew point, and the solid red line is temperature, and this blue dotted line that goes around between the blue line and the red dotted line is your air parcel with CAPE in it. And these numbers are measured in millibars and how close to the ground. For example, like 1,000 millibars is like only 300 feet off the ground, meaning it's really close to the ground. So like your capping inversion stops at about 850 millibars, which is about 2,200 feet above the ground. And it also will tell you here in the sounding your lapse rates, which are lapse rates. Here you go. Right at the bottom it says red, which is 8.3 degrees Celsius per square kilometer, which is a lot. I would need to pay attention to hail that day, and lightning specifically for that. Although, and you can also look at in the purple is where it is launched, and as it curves and goes and does all this snaking stuff, it's going up into the atmosphere. It's like looking down at it, and it's showing what it's doing as it goes up, how it curves and moves and stuff. And that is extremely useful when trying to forecast for like a supercell's updraft, because it's going to curve and do all sorts of cool stuff. And here we continue, and the SARS sound analog system will go through all sorts of different scenarios and older scenarios from different scenarios, and it will look at the past scenarios and what happened in these scenarios and compare them to what is forecasted in the said sounding, and it will give you matches and stuff. So for example, here we have a match from June 19th. I'm gonna assume that probably means 1994, and this is I don't know this very well, but it's like saying there's a match for like baseball size hail, which is 2.75 inches in diameter. And we're going to come back to the photograph here, and this, the 0 degrees Celsius, and then the negative 20 degrees Celsius, and negative 30, this number right here is measured in meters above the ground. And usually for a lowered freezing level, and if you have a lowered freezing level and lots of lapse rates with strong cape, you're going to have more of a severe hail threat. And for example, my negative 20 degrees Celsius mark here is at 25,449 meters above the ground, which is higher. And I'll also note here too on the photograph, you want your red line, your solid red line, and your solid green line to be as close as possible, which is going to increase the relative humidity and enhance lift so you can get stronger updrafts with the cape. And that is very important when forecasting for evening storms, especially in hilly terrain, which is what I have to live in. So in general overview, what you need for a storm is you need instability, you need moisture, you need lift, and you need shear. And combine all those and you will get a storm of some kind, and it will be determined by that storm kind will be determined by the upper level winds and upper dynamics. I hope this has been a good forecasting video, and I hope to see you guys in the next video.